Hi all, welcome to another video of linear control system based on KTU syllabus. Now we are going to discuss some problems based on this Nyquist stability criterion. That is, we are mainly focusing on the Nyquist plots. Okay, Nyquist plot. We are calling it as Nyquist plots. And this is the first question. Draw the Nyquist plot of the system whose open loop transfer function is g of s into h of s is equal to k by s into s plus 2 into s plus 10, and determine the range of k for which the closed loop system is stable. So we have to find stability range of k also here. And for doing the problem, actually the Nyquist plot is we are calling the polar plot also as Nyquist plot, but for drawing this Nyquist plot we will not use any graphs. We can simply draw the Nyquist plot in a plain sheet. Okay, and for doing the problem, first initially we have to convert the loop transfer function into the standard form, that is 1 plus. Okay, 1 plus standard form, that is normally we have used in the both plot and polar plot problems. So first one is g of s into h of s k by s into s plus 2 into s plus 10. It is converted into the standard form, that is by taking outside the value 2 and 10 from these two values 2 times. We will obtain it as 0.05 k divided by s into 1 plus 0.5 s into 1 plus 0.1 s. So this is the first step, and after that we have to plot the Nyquist contour in S-plane. Actually in Nyquist plot, okay, Nyquist stability, according to Nyquist stability criterion, if we are having a contour in S-plane, we will be having a contour in g of s into h of s plane, that is f of s minus 1 plane. Okay, f of s minus 1 plane is normally known as g of s into h of s plane. Okay, so normally we will be drawing the corresponding contour in S plane to the g of s into h of s contour in g of s into h of s plane, that is f of s minus 1 plane. Okay, so initially we have to draw the S-plane contour. Okay, so for drawing the S-plane contour, we will be considering the entire right half of S-plane. Okay, entire right half of S-plane, but we have to avoid a small portion in the origin, because in the question itself we know that there is a pole at origin. Okay, there is a pole at origin. So the Nyquist contour on S-plane enclosing the entire right half plane except the origin we have to consider for analysis. Okay, and if we are having 2 or more poles at origin, in that case also we have to eliminate the corresponding origin. Okay, corresponding origin only. Okay, and if you are having a single pole at origin and 2 poles at imaginary axis, okay, some conditions will be there. Okay, imaginary axis poles, so in that case we have to avoid that poles. Okay, we have to avoid that portions for the analysis purpose. Okay, so this is the portion for poles in the origin, and these two for the poles in the imaginary axis. Okay, but here in question only a single pole is at origin, so we have avoided that portion and we have considered the all entire right half of S-plane for analysis. Okay, so from that you can clearly understand that there are 4 sections for this Nyquist contour in S-plane, that is section C1. Section C1 means that is it is from the value of omega from 0 to plus infinity. Okay, plus infinity. That is because here we have eliminated a small portion for our placing our pole at origin. Okay, and we are considering that the radius of that pole is 0. Okay, radius is approximately tending to 0. That's why we are taking the section C1 from 0. Okay, 0 to plus infinity, and another one is plus infinity to minus infinity, section C2. Okay, in a curved manner with a radius of infinity, because we are considering the entire right half of S-plane, entire right half, so we are considering the radius as infinity. Okay, and section C3 is from minus infinity to 0, and then section C4. Okay, section C4 is like that, a small portion with a radius of 0. Okay, a curved portion. So we have to analyze all these four sections for drawing the Nyquist contour in geometry in the Java's plane that we have to draw. Okay. So first we are going to map the section C1. Section C1. Actually, the section C1 is from 0 to infinity, 0 to plus infinity. So when we have learned the polar plot, and that we have learned that the polar plot is drawn from by considering the values of omega from 0 to infinity. Okay, and we will find different we will arbitrarily take some values of omega from 0 to infinity, and for that corresponding value of omega we will find the magnitude and phase angle, and we will draw our polar plot. Okay, so likewise the section C1 is same as our polar plot. Okay, that is we can approximately anticipate the shape of the polar plot based on the type number and order of the system. Okay, so here the type number is 1 and order is 3. So normally our polar plot will be, if you are drawing the polar plot, okay, the approximate shape of the polar plot will be for a type 1 order 3 system, it will be like that. Okay, it will be like that. So the same case we can assume here, but here we have to find the crossing point of this negative real axis, this point. Okay, so for finding that crossing point, okay, we'll consider the g of syntax of a function, and we are assuming that s is equal to j omega. That is same, that is we will find the sinusoidal transfer function by putting s is equal to j omega, and we will arrange our terms, and we will open the brackets, and we will get a last function like that, that is 0.05 k divided by minus 0.6 omega square plus j omega into 1 minus 0.05 omega square. Okay, and we know that this crossing point will be our phase crossover frequency omega pc. Okay, that is corresponding to our gain margin. Okay, that is omega pc. So when the polar plot crosses this point, we know that the corresponding imaginary term, that is j term, okay, the corresponding imaginary term will be 0 because the imaginary axis is this one. So corresponding to this omega pc, the imaginary term will be 0. So here the imaginary term is omega into 1 minus 0.05 omega square. Okay, so that will be equating to 0 here. So we can see that is omega into minus 1 minus 0.05 omega square. So omega is substituted as omega pc, that is phase crossover frequency here. So from that we will get the omega pc as 4.472 radian per second by solving the equation, and we will substitute the value of omega in the g of j omega in touch of j omega equation for the real part. Real part is 0.05 k divided by minus 0.6 omega square. This is the real part. So we will substitute the value of omega in the real part. That is the real part of g of j omega in touch of j omega is 0.05 k divided by minus 0.6 omega square. Okay, and if you are substituting the value of omega as 4.472, here we will get the crossing point. Okay, that omega equal to omega base, the crossing point is minus 0.00417 k. So we are going to map the section C1 into geometry in the Java's plane. So section C1 is from 0 to infinity, that we have drawn in S plane. Okay, that is our first one. Okay, this section C1. Okay, and we know that it is a type 1 order 3 system based on the function given, type 1 order 3 system. So the graph will be like that. Okay, so here the corresponding mapping in geometry in the Java's plane is like our polar plot. Okay, this is the mapping for section C1, and this crossing point is minus 0.0417 k. This is the mapping. Okay, and after that we have to map the section C2. Here the section C2 is from plus infinity to minus infinity. That is, if you are saying the angle, okay, the C2 will change from plus 90, plus pi by 2 to 0, then minus pi by 2. That is plus pi by 2 to minus pi by 2. The changes from plus pi by 2 to minus pi by 2, if you are saying in terms of angle. Okay, so mapping of section C2. The mapping of section C2 from S plane to geometry in the Java plane is obtained by letting the value of S. Okay, by letting the value of S is equal to limit r tends to infinity r into e raised to j theta. Okay, we are substituting the value of s as limit r tends to infinity r into e raised to j theta. Okay, that you can see here. This time is that here the r tends to infinity means because here the radius of the section C2, listen carefully, the radius of section C2 is infinity because we are considering the entire right half of S plane, so the radius will be infinity. Okay, so here the radius of the small half circle is 0. Okay, so for mapping section C2 we are letting S is equal to limit r tends to infinity r into e raised to j theta in the g hours in the hours. Okay, and we know that the angle is varying from plus infinity to minus infinity, that we know. Okay, sorry, angle is varying from plus pi by 2 to minus pi by 2. Okay, that is, if you are choosing the geos in the hours, that is 0.05 k by s into 1 plus 0.5 s into 1 plus 0.1 s. If you are letting s is equal to r tends to infinity, okay, here it is r tends to infinity, so the 1 plus st times, okay, here in the question it is 1 plus 0.5 s, 1 plus 0.1 s. Okay, if the term s tends to infinity, we know that this 1 plus 0.5 s we can simply write it as 0.5 s instead of this 1 plus 0.1 s if s tends to infinity. Okay, here because the r is tending to infinity here, so s will always be tending to infinity, so 1 plus 0.1 s can be written as 0.1 s. So the time is 0.05 k divided by s into 0.5 s into 0.1 s by is equal to k by s cube. This is our g hours in the hours. Okay, and we are substituting the value of s as limit r tends to infinity r into e raised to j theta instead of this s. So k divided by s cube at s equal to r tends limit r tends to infinity r into e raised to j theta, so k by limit r tends to infinity r into e raised to j theta all cube because it is s cube, so r into e raised to j theta all cube. And we know that if r tends to infinity, this the r is in the denominator term, so the magnitude will be 0, the magnitude will become 0, and the phase angle, that is e raised to j theta cube. Okay, so it will become e raised to minus 3 j theta. Okay, e raised to 3 j theta is in the denominator, so if you are taking in the numerator, it will become e raised to minus j3 theta, so the magnitude will be 0 and the angle will corresponding to e raised to minus j3 theta. Okay, and we know that the theta, the value of theta is varying from pi by 2 to minus pi by 2, pi by 2 to minus pi by 2. We know that the variation in angle, okay, if you are considering the quadrants, this is the 0 degree, this is the plus 90, this is the plus 180, and this is the plus 270, this again plus 360 or 0. Okay, this plus 360 or 0, and if you are taking the negative reverse side, that is 0 minus 90 minus 180 minus 270 minus 360, like that. So this is the angles corresponding to each quadrant. Okay, so here the section C2 is varying from this, okay, this axis to this axis, so it is plus 90 axis, this is plus 90 axis. Okay, so plus 90, it comes to 0, then again minus 90. Okay, plus 90, 0, minus 90. Okay, so pi by 2 to minus pi by 2 is varying, so we are substituting the value of theta to the theta here, that is g in the hours as 0 into e raised to minus j 3 pi by 2, theta is pi by 2, and for theta is equal to minus pi by 2, here the equation will be g in the hours will be 0 e raised to plus j 3 pi by 2. Okay, that is theta is minus 3 pi by 2, sorry, minus pi by 2. So if you are substituting the minus pi by 2 here instead of this theta, it will become plus j 3 pi by 2. Okay, so the corresponding contour in geos in the hours plane will vary from minus 3 pi by 2 to plus 3 pi 2, that is minus 272 to plus 270 with a radius of 0. Okay, so we are going to map the section C2. So the corresponding section in S plane is, we know that it is the mapping in S plane. We are going to map this section C2 into this geos in the hours plane, and we know that for mapping this C2, the radius, okay, the magnitude is 0. Okay, and the corresponding phase angle varying from minus 270 to plus 270. We know that the minus 270, where is the point minus 270? That is minus 270. We know that this is 0, minus 90, minus 180, minus 270. Okay, so we have to start from okay, this axis. So minus 270 to plus 270. So the corresponding marking will be minus 270, then minus 180, then minus 90, 0, then again plus 90, plus 180, plus 270. Okay, this is the direction. Okay, so this will be the corresponding contour in G of S into H of S plane. Okay, so listen carefully. Here the magnitude is 0. Okay, so the radius here it will be 0, and the angle is varying from minus pi by 2 to plus 3 pi by 2. So minus 3 pi by 2 to plus 3 pi by 2. So minus 3 pi by 2 is here. So minus 3 pi, that is minus 270. Okay, minus 270 is here. So minus 270, minus 180, then minus 90, 0, then plus 90, plus 180, plus 270. Okay, this is the corresponding contour in G of S into H of S plane. Okay, so you can see here with axis U and JV, the corresponding contour in G of S into H of S plane is like this. Okay, and next one is the mapping of section C3. We know that the mapping of section C3 is entirely opposite to the C1. C1 is from 0 to infinity, C3 is from minus infinity to 0. So we can draw the entirely opposite graph of C1. Okay, the corresponding contour in G of S in the H of S plane corresponding to this section C1 is like this. Okay, so the corresponding contour in G of S in the H of S for section C3 will be entirely opposite of this graph. Okay, so we can draw the graph as entirely opposite to our section C1. Okay, no more further calculation is needed here. We can simply draw the graph with the same crossing point of minus 0.00417 k. Okay, just opposite to that section C1. Okay, this is the corresponding mapping of section C3, and the last one is the mapping of section C4. So here the section C4 is from, if you are observing the figure, section C4 is from like this. That is, we can say that section C4 is from minus pi by 2 to plus pi by 2. Okay, that is minus pi by 2, 0, plus pi by 2. Only a single encirclement is here. So minus pi by 2, 0, plus pi by 2. Okay, so here section C4 can be mapped as, we are for the curved nature, for the curved sections, we are always assuming that the value of S as like this. So here the radius is 0, that is a small circle we are considering. Okay, that is of radius 0. So S10 is equal to limit r tends to 0, r in d raised to j theta. Okay, and we know that if r tends to 0, the corresponding value of, if we are having a function 1 plus 0.5s, if this r tends to 0 means s tends to 0. Okay, so the 1 plus 0.5s becomes only 1. We can simply eliminate the value 0.5s because here the value of s is tending to 0. Okay, so 1 plus st we can simply write as 1. So the G of S in the H of S can be written as 0.05 k divided by s into 1 into 1. That is 0.05 k by s. This is the G of S in the H of S corresponding to section C4. And we know that we are going to put the value of s as limit r tends to 0, r into ratio theta. Okay, so here 0.05 k divided by limit r tends to 0, r into ratio theta. So the power of s is 1, so we can simply write r into ratio theta alone. And if you are putting r tends to 0, the r is in the denominator side, so the entire value become the magnitude will become infinity, and the phase angle is corresponding to e raised to j theta. So we know that the theta, so for section C4, the theta is varying from minus pi by 2 to plus pi by 2. Okay, minus pi by 2 to plus pi by 2. So for theta is equal to minus pi by 2, the corresponding G of S in H of S will be infinity e raised to minus j theta. So theta is minus pi by 2, so it becomes e raised to plus j pi by 2. For theta is equal to pi by 2, G of S in H of S become infinity into e raised to minus j pi by 2. Okay, So for plotting the section C4 into the geocentric plane, we know that the corresponding radius will be, the magnitude will be infinity, and the phase angle is varying from e raised to plus j pi by 2, that is plus pi by 2 to minus pi by 2 is the variation. Okay, so this is the corresponding contour in S plane, and if you are plotting the corresponding contour in f of s plane, f of s minus 1 plane, that is g of s in h of s plane, we know that the phase angle is varying from plus pi by 2. So plus pi by 2 is here, plus pi by 2 to minus pi by 2. So plus pi by 2 0 minus pi by 2, and the radius is infinity. So this is the corresponding plotting for C4. Okay, and after that, at last we have to combine all these four sections together. Okay, so the first section is, this is the first section. Okay, this is the first section. So we will start drawing from the first section itself. So this is the first section, and the section second section is this one. So of radius 0, here the radius is 0. Section C2, the radius is 0. Okay, you can see this is the section C2 corresponding to the section C2 in S plane. Okay, in geocentric plane, this is the corresponding plot. So here the radius is 0. Okay, so we can continue the graph as like this. Okay, this is the section C2, and for section C4 it is like this, from this to this line. Okay, so if you are drawing that, if you are from this value, we will go like this. Okay, and the last one is this one. Okay, we can clearly see that graph in the next slide. This is the graph and their plot of Nyquist plot. Okay, so listen carefully. This is the section C1, plot for section C1, and section C2 is of radius only 0, so it is like that. Okay, that is plus 270 to minus 270, and again the section C3, then the section C4. This is the plot for this actual Nyquist plot corresponding to geos and hos. Okay, and also for finding the value of k. Okay, listen carefully. For value of k, that is, we are assuming that the closing point here is minus at minus 1 plus j0. We are assuming that this minus 0.00417 k is minus 1 plus j0. So when this minus 0.00417 k is equal to minus 1, the corresponding value of k will be 240. Okay, and we will be considering some ranges of k. Okay, when k is less than 240, what happens? That is, this crossing point will be, okay, between this 0 and minus 1 plus j0. Okay, that is, we are assuming that this crossing point as minus 1, and corresponding to that assumption, the value of k is obtained as 240. If the value of k is less than 240, okay, the contour crosses real axis at a point between 0 and minus 1 plus j0. Okay, so on traveling through the Nyquist plot, okay, along the indicated direction, it is found that the point minus 1 plus j0 is not encircled. Okay, so that is for k less than 240. For k less than 240, the minus 1 plus j0 will be here. Minus 1 plus j0 will be here. That is, our this crossing point will be less than this minus 1 plus j0. Okay, when k is less than 240. So this Nyquist contour will not encircle the point here. Okay, so we can get as an assumption that the Nyquist plot will not encircle the point minus 1 plus j0. Also, the open loop transformation has no poles on the right half of S plane. So this is the open loop transformation. Here the poles are s is equal to 0, s equal to minus 2, s is equal to minus 10. So no poles are on the right half of S plane. Okay, so according to Nyquist stability criterion, we can say that the closed loop system is stable for the range of k less than 240. And when k greater than 240, what happens? The contour, okay, when k greater than 240, the crossing point will be, okay, this crossing point will be between 0 and that is this crossing point will be between minus 1 plus j0 and between minus infinity. Okay, that is here the value of k is greater than 240. Okay, so of course the point minus 0 0.00417 k will be greater than this minus 1 plus j0. Okay, so the contour crosses the real axis at the point between minus 1 plus j0 and minus infinity. Okay, and if you are, this is the corresponding point here for k greater than 240, minus 1 plus j0 will be like this. So on traveling through this Nyquist contour, we know that this Nyquist contour will encircle this point. Okay, encircle the minus 1 plus j0 point. This is the first encirclement and this is the second encirclement, two times. Okay, two times in the clockwise direction. Okay, so two times in the clockwise direction. And here, since there are two clockwise encirclement and no right half of open poles, the closed loop system has two poles on right half of its plane. Therefore, the closed loop system is unstable. So, for the stability of the system, the value of k will be between 0 less than k less than 240. Okay. So, I hope all of you understand the problem.